Hello everyone, welcome back. In this video, we'll be taking a look at bounded sequences. So what's a bounded sequence? So a sequence is said to be bounded if there exists a number m such that a positive number m greater than 0, such that all the sequence terms are less than or equal to that number m. So that means we can find an interval which is minus m below and m above, such that we can find all the sequence terms in between this interval. So let's take a look at this visually to see really what's happening here. So if we have a sequence this way, then it converges. So we say this sequence is bounded because we can find a number m right here and one right here. This is positive m, negative m, because we can find this number m such that all the sequence terms are either are in between these two numbers. So all the sequence terms are either less than or equal to this m, which is greater than 0. So we can find all the sequence terms in between this interval, in between these barriers or in between these walls. So we say a sequence is bounded if we can find a m such that all the sequence terms are between these two. So let's take a look at one interesting theorem that we can get from this. So every convergent sequence, so if a sequence converges to a limit, or a sequence has a limit, if a sequence tends to a limit, so every convergent sequence, in short, is bounded. So let's see the proof of this theorem. So where do we begin? So let's take a look at this graphically to see what's really happening here. So we have a sequence right here that converges to the limit L. So if it converges, it enters a tube. It enters a tube L plus epsilon and L minus epsilon, and it never leaves this tube. Right, that's what convergence means. So that's L plus epsilon and L minus epsilon, L plus epsilon, L minus epsilon. So see, we say a sequence converges if it enters this tube and never leaves, if it eventually enters this tube and never leaves this tube. And here we have the capital N. So after this capital N, all small n, all the sequence terms, or the distance between the sequence terms and L is less than epsilon. Well, so for example, if we take epsilon equals to 1, so if we replace this epsilon by 1, so we get it as L minus 1 and L plus 1, then we know there exists an n such that for all n greater than n, since the sequence is converging, we know that it enters this tube and never leaves this tube. So we can find an n such that all sequence terms enter this tube L plus 1 and L minus 1 and never leave this tube again. So we can say that all sequence terms after certain time, all the sequence term are less than modulus L plus 1. We use modulus L because we don't know, sometimes this L may be positive and sometimes it may be negative, right? So this is a good candidate for our bound. We can say this L plus 1, which is this one right here, is a good candidate for our bound. So that completes the proof. So I hope you guys are getting this. Let me repeat it one more time. So since we know this is a convergent sequence, we are assuming this is a convergent sequence. Since it's a convergent sequence, we know it tends to a certain number L. And since it tends to a certain number L, from the definition of the sequence, we can find some n, and we can choose from the definition of a sequence, we know for all epsilon greater than 0, there exists an n such that a n minus L is less than epsilon. And since we know this is a convergent sequence, since we know this is a, sorry, epsilon should be this way, since we know this is a convergent sequence, and therefore it's true for all epsilon, for any value of epsilon. So right here I'm choosing epsilon to be 1. So if we take L plus 1 and L minus 1, there is some n, we don't know what n because this is an arbitrary sequence, but since it's a convergent sequence, there is some n, there is some n, it's guaranteed to be there, such that it enters the tube L plus 1 and L minus 1 and it never leaves the tube. So L plus 1 right here is a good candidate for our bound, but we still need to worry about these sequences which are to the left of n, these sequences right here. So we're lucky. So we know for this sequence, it's guaranteed that L plus 1 is a bound. No sequence term right here can go above L plus 1. We can never find any sequence terms such as this right here, because we know that they'll never leave this tube. They'll never leave this tube L plus 1 right here. So we know there'll never be any sequence terms that are above this L plus 1. So L plus 1 is a good enough bound for this. But now consider such this sequence right here, which I'm gonna use green for. Consider this green sequence right here, which goes somewhere like this. And right here, this is the L. And this is the L plus 1. And this is the L minus 1. So right here, if you notice that after some time there is an n right here. After this n, since it's a convergent sequence, we can't find any sequence such as this. We can't find any sequence terms that are greater than L plus 1 after this n. So these sequence terms do not exist. Let me draw that L plus 1 right again. So there are no sequence terms such as these ones or these ones. These sequence terms do not exist because after this n, all of them enter this tube and never leave this tube. So they're all less than or equal to this epsilon, which I chose as 1. So they're all less than or equal to L plus 1. But then but in this sequence, in this green sequence, L plus 1 is not good enough of a bound for us, because we see this x1 right here, we see this x2 right here, we see this x3 and x4, which are all greater than L plus 1, and therefore L plus 1 can't be a bound for here, because remember, a bounded sequence is a sequence in which all the terms of the sequence are contained in this interval. So if we choose L plus 1 as a bound, it does not contain all the sequence terms, as in it does not contain all the sequence terms. Remember the bound from the previous part. A bound M is a bound if and only if there if all sequence terms are less than or equal to m. Right here, L plus 1 can't be a bound for this green sequence, because all the sequence terms, only some of the sequence terms, specifically only terms after n, are less than or equal to L plus 1. The sequence terms x1, x2, x3 and x4 are not less than or equal to L plus 1. So therefore we choose M so therefore to be safe, let's go back and write the proof for this. We choose M to be the max, to be the maximum, whatever is the maximum of x1, x2, so on and so forth, up till xn minus 1, and then L plus 1. So let me explain. So in this green sequence, x1 will be the bound, because if we choose x1 to be the bound, this is the, let me use a different color. This colorful line is the x1. So we choose x1 to be the bound. We know that all sequence terms are less than or equal to this x1. So x1 is the bound because it's the maximum. But however, if we consider this sequence, which I'm going to draw right here, it goes like this. This is x1 and this is x2. This is x3, and then it converges again to L. In this scenario, the maximum is x2. Therefore, x2 will be the bound, because after x2, because all sequence terms are less than or equal to x2. But then remember, in the first sequence we considered right here, L plus 1 is the maximum. L plus 1 is the maximum, and therefore L plus 1 is the bound for this first sequence we considered, because all the sequence terms are less than L plus 1, because after n all the sequence terms enter this tube and never leave this tube. So all the sequence terms are less than L plus 1. X1 is less than L plus 1, x2 is less than L plus 1, xn minus 1, which is the term just before this n, just before the sequence begins to enter the tube, is also is less than L plus 1. Therefore, in this case, L plus 1 is the bound, whereas for this green case, for this green sequence, x1 is the bound, and for this sequence, x2 is the bound. Therefore, this single line is just the proof of this theorem. Let M the bound, where M is the bound. Remember that M is the bound. So M is just the maximum of x1, x2, or xn minus 1, where n is the term after which all the sequence terms enter this tube, and L plus 1, where L is the limit of the sequence. So hope you guys enjoyed this video. See you next time.